2011 was an exciting year for astronomers. For over 200 years, mankind had known about the existence of gigantic asteroids found in the asteroid belt. But for most of that, they've only been specks in the night sky. The first asteroid to be discovered, Ceres, was found in 1801 and was added to the list of planets. A year later, Pallas was discovered, and in the following years, Juno and Vesta. Because of this, in 1845, our solar system had 11 planets, the original 7 from Mercury to Uranus, as Neptune hadn't been discovered yet, plus the 4 asteroids. As more and more asteroids were discovered, it became clear they couldn't all be listed as planets. A good thing, too, as today, there are millions of known asteroids of various shapes and sizes. However, before 2011, we had never seen any of the original 4 asteroids up close. Enter the Dawn spacecraft. Launched in 2007, it had a very special mission: to explore and investigate not just one, but 2 of these large asteroids. First Vesta, and then Ceres. But what did it find and discover while it was there? Welcome to this cosmic journey with us. In this video, we will find out everything Dawn saw and discovered around the asteroids Vesta and Ceres, and examine what made the Dawn spacecraft one of the most technically impressive probes ever produced, and how its success paved the way for NASA missions in production right now. Let's start with Dawn itself. Its trip to Vesta took 4 years, utilizing a slingshot from Mars's gravity along the way. And you'll be forgiven for not seeing anything special about this trip from this perspective. However, zooming in on the Dawn spacecraft itself reveals its very special feature: an ion engine. Ion engines had been tested already on NASA's Deep Space One. However, the way Dawn utilized it pushed this technology to a whole new level. Thanks to its ion engine, it was the first ever spacecraft to go into orbit around 2 separate extraterrestrial bodies. You see, while ion thrusters aren't very powerful, they are extremely efficient, and so can remain on for extended periods of time. Unlike chemical thrusters, which rely on reactions causing heat and pressure to push gas away from the rocket, ion thrusters simply ionize neutral xenon gas with electricity to create acceleration. These ionized gas particles rush out of the engine at 150,000 kilometers per hour, which pushes the spacecraft in the opposite direction. As the ionized gas is expended slowly, Dawn can only create so much electric charge after all. The acceleration is really slow. It would take Dawn 4 days to accelerate from 0 to 100 kilometers per hour. But over extended periods, it really adds up. Dawn was firing its thrusters for 85% of the time during the transit to Mars, expending only 72 kilograms of xenon propellant, and gaining over 1.8 kilometers per second velocity. Upon reaching Vesta in July 2011, the images it started returning wowed the science community. It really was not what they were expecting. After being captured by Vesta's gravity, Dawn lowered its orbit to get a closer look at this unique asteroid. So, what made Vesta an unexpectedly nice surprise? The first thing you'll notice about Vesta is that it has an unusual shape. It kind of looks like a squashed ball. There are 2 reasons for this. The first is that it is not very big. Yes, these asteroids, although big for asteroids, are pretty tiny on astronomical scales. Vesta is not quite big enough for it to be in hydrostatic equilibrium, or in other words, to be rounded by its own gravity, as it is only about 500 kilometers in diameter. This gives it the surface area of Pakistan, about 800,000 square kilometers. You'll see how small it is if you compare it to our moon. Although it should be noted that even at this size, it still contributes towards 9% of the total mass of the asteroid belt, which can help you appreciate just how dispersed the asteroid belt really is. The second reason for this unusual shape is the 2 giant impacts it experienced in its past. Estimated to have occurred over 1 billion years ago, Vesta was impacted not once, but twice around its south pole with planetary-scale objects. These impacts produced craters so large, they penetrated all the way to the mantle of the asteroid. If you enjoyed this video, please give it a thumbs up and hit that subscribe button for more. The crust has since cooled off and solidified, leaving a complex crater called Rhea Silvia. As these craters have overlapped, Rhea Silvia is the most recent and thus the most prominent crater that remains. As is typical with complex craters, terraced walls can be seen around the edge of the crater, seen in the form of huge troughs around the equator that put the Grand Canyon to shame in terms of size. Also typical of complex craters, a prominent peak can be found at the center. This peak was once thought to be the tallest mountain in the solar system, but more accurate dawn observations shows that the title has returned to Olympus Mons, although Rhea Silvia is still 20 to 25 kilometers high and over 100 kilometers across. Due to its size compared to the size of Vesta, it appears like a giant pimple around the South Pole, and it is easily visible from orbit. The two collisions that carved out the South Pole of Vesta flung a massive amount of ejecta into space. So much debris ended up in the asteroid belt that this debris has been given its own asteroid spectral type classification, namely V-type asteroids. V-type asteroids are thought to have originated from Vesta, and a lot of them can be traced back to those impacts. But these asteroids didn't just end up in the asteroid belt. They are scattered all across the solar system, and in fact, 5% of the meteorites that end up on Earth come from Vesta, known as Howardite-Eucrit diogenite meteorites. This is very handy, as we haven't needed a sample return mission to be able to study samples of Vesta, because Vesta has delivered some right to our front door. Their structure and composition reveal some clues about how Vesta was formed, and the Dawn mission attempted to broaden that understanding. From a combination of all the data collected, it has been revealed that Vesta is very unique in our solar system. It is the only remaining rocky protoplanet, or in other words, it is a planetary embryo that never finished forming. The theory goes that as the solar system was forming, dust from the early protoplanetary disk coalesced into thousands of different planetesimals. These planetesimals collided with each other over time, building up into the large planets we see today. Our moon is thought to have formed from such an impact with a large planetesimal impacting Earth, called Theia, the debris from the collision coalescing in Earth's orbit, and over time rounding under its own gravity to form the moon we know today. Vesta obviously got started on its way to becoming a planet. It experienced plenty of large impacts with planetesimals. As a result of all these impacts, the heat generated by them meant that at one point, Vesta had an active mantle under the surface. Even today, it is believed to still have a core of iron about 220 kilometers in diameter, a core similar to the other terrestrial worlds like Mercury, Venus, Earth, and Mars. However, Vesta's interior has since cooled off, meaning the interior has solidified. But because of this differentiated interior, it likely would be called a dwarf planet today, if not for those two collisions we talked about earlier. One of the criteria for a dwarf planet is that it is rounded under its own gravity. But as the collisions happened roughly 1 billion years ago, a few billion years after Vesta formed, Vesta had already cooled off too much for it to be elastic enough to return to a shape in hydrostatic equilibrium. And the reason Vesta never became a planet? Fingers are currently being pointed at Jupiter, which stole mass that would have otherwise formed Vesta, or at least disturbed enough of it to stop Vesta from ever getting going. Now, to the naked eye, Vesta does appear quite bland. This is a true color image of Vesta, appearing as you would see it. However, if you have a camera that can see in a wide variety of wavelengths of light, suddenly Vesta's true variety becomes apparent. In this composite image, The black material is likely ejecta brought by a large meteor impact. The red material is likely also from an impact, but material that melted before solidifying again. Dawn also made some unexpected discoveries on Vesta's surface. Vesta is thought to be very dry, with little to no volatiles found in its crust. Why then has evidence of past flowing been observed? In this false color image, you can see a crater a couple of kilometers across, with a flow channel coming out of it. The different colors indicating it consists of a different material to the surrounding area. The exact origin of this material is unknown, but perhaps it was brought by the impactor and melted on collision. Another fascinating discovery was found in one of Vesta's youngest craters, Marcia. Near the bottom of the crater, Dawn observed something called pitted terrain. Why pitted terrain was found of Vesta is a bit of a mystery, as we had only seen it on Mars before that. However, scientists believe hydrated mineral rocks on the surface may have been rapidly heated, perhaps by another impact, releasing the water in the rocks, which exploded as the water degassed into space, leaving these craters you see here. And I would be remiss to mention that this Marcia crater is part of a chain of craters which makes up the famous snowman found on Vesta. What is interesting though is if you notice the terrain is relatively smooth around these craters. That is believed to be because a blanket of ejecta covered the region from the impacts, smoothing it over. Dawn was only around Vesta for a year before it left Vesta's orbit and moved on to the second leg of its journey towards the actual dwarf planet, Ceres. Using its ion engine, it was able to build up speed until it was finally fast enough to escape Vesta's gravity altogether, and then begin its journey towards Ceres. The anticipation within the scientific community to reach Ceres was palpable. Even with the aid of the Hubble Space Telescope, the best image we had of Ceres was this. Would Dawn hold up to years in the unforgiving environment of space? And what would Ceres reveal about our own solar system? After 2 years in transit between the two bodies, Dawn finally began the approach to Ceres. As days passed, the resolution of Ceres got better and better. Details like craters could finally be resolved, and most interestingly of all, bright white dots could be seen. I remember at the time that, as these images were coming in, speculation was rife about what they could be. As higher resolution images were received, it looked like the brightest spot was actually 2 separate spots, and then the increased resolution revealed it was in fact several different spots. Dawn also observed the scarred nature of Ceres up close, with craters littering the surface. Although, there aren't as many craters here as previously expected. Taking this into consideration and the bright spots I already mentioned, it became clear that Ceres is not as inactive and inert as we may have previously thought. Before we delve deeper into that, let's first give you some context. Ceres is a very unusual body, seemingly out of place in the asteroid belt. Most asteroids are mainly composed of non-volatile substances, mainly rocks and metals. Ceres, on the other hand, has a similar composition to that of a comet. It is, in other words, an icy world. However, being this close to the Sun, any ice directly on the surface sublimates. This means that the surface crust is rocky, yet porous, with water locked into the gaps, with a ratio of about 90% rocks and 10% water. Beneath the surface, there is believed to be a muddy mantle and a large core of hydrated rocks, such as clays, where rock and brine are mixed together at a 50-50 ratio, although this has been hard to confirm. Other models suggest the core could be a lot drier and smaller, with a greater ratio of water to be found in the mantle. Either way, water is definitely present in Ceres in large quantities, making up perhaps 50% of its total volume due to Ceres' low density. And it's this water that perhaps renews the surface of Ceres, albeit over extremely long timescales. You see, these bright spots are what is known as cryovolcanoes. Unlike regular volcanoes, which spew lava out from the mantle, cryovolcanoes erupt water. This is a 3D model based on dawn data of the biggest bright spot on Ceres. Water on Ceres is packed full of salt, meaning that when a cryovolcano on Ceres erupts, the water sublimates, and the salt is left behind. This was directly observed over the brightest patch on Ceres, known as Spot 5, as a haze was periodically seen over this area, indicating that water there had sublimated. These bright spots darken over time from exposure to the sun through space weathering, so it's likely that many old cryovolcanoes exist on the surface of Ceres, although we can now only see the most active and most recent ones. If you found this interesting, leave a like and subscribe to join our space-loving community. However, the ones we can see aren't just limited to just the bright spots we've looked at so far. There are many of them dotted around the dwarf planet. Water was discovered in other regions around Ceres too. Due to Ceres' very minimal axial tilt of only 4 degrees, some craters at its poles are in perpetual darkness. The bottom of these craters never see direct sunlight, meaning water ice can exist here without sublimating. This is very similar to our moon, where water ice is also thought to have been trapped at the bottom of perpetually dark craters for billions of years. What else did dawn spot on the surface of Ceres? As I mentioned, it saw plenty of craters, each with unique characteristics. Some were very round and defined. Others had scarps along the crater floor. There were plenty of examples of complex craters, with tall peaks in the center. There was even evidence of crater rims collapsing. For example, this rock having fallen away from the crater walls. Smaller rocks were also spotted having fallen down crater walls, evidenced by the trails they left behind. I also love these photos taken at an angle, pointed along the limb of the dwarf planet. To me, these give a much better idea of the scale of the features we are looking at. Although without an atmosphere to provide a sense of depth, it's hard to judge sizes in images like these. Fractures were also spotted all over Ceres, indicating there have been stresses in the crust. Some of them are relatively young, perhaps only a few 100 million years old. Some of them come in the form of grooves and troughs, where the crust has been stretched, and other fractures can be seen in the form of rows of mountains, where the crust has been compressed. One particularly unusual feature was spotted on Ceres, called Ahuna Mons. It's a mountain about 20 kilometers wide and 5 kilometers high, but what's unusual about it is how it just sticks up from the surrounding area, with no apparent cause. It would be less unusual if there were other features like this on Ceres, because then it could be said that it's a global phenomenon, but it's the only thing like it on the entire world. The best bet we currently have is that it is an old cryovolcano, formed because of a large impact directly on the other side of the dwarf planet. Seismic waves from large impact can propagate through the crust of a planet, and where the waves meet again on the opposite side is known as the antipode. Known antipodal regions around the solar system tend to have some kind of weird terrain, like that found on Mercury. Ahuna Mons could fit this description, with seismic waves from an impact on the opposite side of Ceres triggering volcanic activity here. If it is a cryovolcano, it actually has some analogs around the solar system. It would be classified as a dome volcano, similar to Mt. St. Helens, or to some domes seen on Mars. In 2018, Dawn concluded its mission, having been a tremendous success. It finally ran out of propellant, which meant it could no longer stay pointed at Earth to send back data or receive commands. It's been left in a stable, derelict orbit around Ceres, a monument in space that will remain there for at least another 20 years. Dawn's discoveries and data will remain the foundation for asteroid research for many years to come. But it also leaves behind another legacy. Its ion engines were the key to Dawn's success, and now there are many other missions using this technology. SpaceX's Starlink satellites are all equipped with ion thrusters, as is China's Tiangong space station. ESA's Bepi-Colombo mission is using ion engines to travel to Mercury, and NASA's DART mission is using this technology to reach the binary asteroid system Didymos and Dimorphos. If you want to learn more about that, in my opinion, truly fascinating mission, check out the video I made about it here. Thanks so much for watching. Don't forget to hit like, share, and subscribe so you never miss out on our next exciting videos. Wishing you all the best, and see you next time on our next adventure.